Good morning, students. Our next theorem is Hausdorffness of quotient space. Let us take X to be a topological space and the space quotient space, which is denoted by X by R with topology tau R. This topology is quotient topology. If this quotient space is T2 space, then the relation R is closed in X cross X. And in the second part, we proved that if the relation R is closed in X cross X and the mapping Q from X into X by R is open, then the quotient space is Hausdorff space. So first of all, let us define the mapping Q from X into X by R by taking an element X from here, and then if we take an element X from the set X, then its equivalence class is denoted by the element Rx. So we can define the mapping Q by Q of X is equal to Rx. Here X is the element of X. Rx is equivalence class of X. So by definition of equivalence class, this is the collection of all those elements of X which are related to X. Means the collection of all those Y which are the elements of X and Y is related to X. Now X is related to Y if Qx is equal to Qy. Now Qx is the equivalence class of X and Qy is equivalence class of Y. So we can say that X is related to Y if equivalence class of X is equal to equivalence class of Y. So in this way we have defined the relation R. Now first of all, let us suppose that the quotient space X by R is T2 space, and we prove that the relation R is closed in X cross X. In order to prove that the relation is closed, let us take an element xy belonging to the set X cross X such that this ordered pair does not belong to R. Now we claim that this ordered pair consisting of elements X and Y does not belong to closure of R. Now because this ordered pair xy does not belong to R, it means by definition X is not related to Y. So by definition of relation R, equivalence class of X is not equal to equivalence class of Y. Now because Rx and Ry, these are the elements of the quotient space X by R, and these two elements are distinct elements, and we are given that the quotient space is T2 space. So by definition of T2 space, distinct elements of this space will have disjoint neighborhoods. So there exists a neighborhood H of Rx and K of Ry such that intersection of these neighborhoods is phi. The neighborhood of Rx we have taken as H, the neighborhood of Ry we have taken as K. So H intersection K is phi. Now because H and K, they belongs to the quotient topology to R, it means H and K are open in X by R. So by definition of quotient topology, their inverse image under Q will be in the topology tau. It means Q inverse H belongs to tau and Q inverse K belongs to tau. Let us denote Q inverse H by A and Q inverse K by B. So from here we have obtained A and B belongs to tau. Therefore we can say that their Cartesian product is open in X cross X. Now because the equivalence class of X that belongs to H and equivalence class of Y belongs to K. Now by definition this is Q of x. So from here we can say that Qx belongs to H, and from here we get Qy belongs to K. And this further implies that x belongs to Q inverse H and y belongs to Q inverse K. This is A, this set is B. So x belongs to A, y belongs to B. Therefore, the ordered pair formed by x and y belongs to A cross B. So from here, because A cross B is open, it is neighborhood of each of its points, and this is the point of A cross B. So we can say that A cross B is neighborhood of the point xy. Now next we claim that A cross B intersection with the relation R, that is empty. We prove it by contradiction. Let if possible, the intersection of R with the Cartesian product of A and B is non-empty. So we can take an element, that element we have taken as the ordered pair x star y star. This belongs to the intersection of A cross B with R. Now by definition of intersection, this element belongs to A cross B as well as R. Now because this ordered pair belongs to A cross B, so by definition of ordered pair, this x star belongs to A and y star belongs to B. Substituting the values of A and B here, it means x star belongs to Q inverse H and y star belongs to Q inverse K. So from here, image of x star under Q belongs to H and image of y star under Q belongs to K. Now by definition, this is Rx star, so Rx star belongs to H. This is Ry star, so from here we get Ry star belongs to K. Now by using this definition, because the ordered pair consisting of x star and y star belongs to the relation R, so by definition of relation R, their equivalence classes will be same. So the equivalence class of x star is equal to equivalence class of y star. So we can say that equivalence class of x star belongs to H intersection K. But this is a contradiction because we already discussed the intersection of H and K, that is empty. So this contradiction proves that our assumption is wrong. So A cross B intersection R is empty. It means this ordered pair consisting of x and y is not a closure point of R, and this proves that the relation is closed. Now we prove the converse part. In the second part, we are given that the relation R is closed in x cross x and the mapping Q from x into x by R is open mapping, and we prove that the quotient space is T2 space. In order to prove that the quotient space is T2, let us take two distinct elements Rx and Ry belonging to this quotient space. Now, because these two elements are distinct, so by definition of relation R, if Rx is not equal to Ry, it means the ordered pair consisting of x and y does not belong to relation. Now because the relation R is closed, it means R closure is same as R. It means this ordered pair does not belong to R closure. It means this ordered pair is not a closure point of R. So by definition, the intersection of R with the neighborhood of this ordered pair, that will be empty. So we can take a neighborhood of this ordered pair. The neighborhood of this ordered pair will be of the form of A cross B, where A and B are form the topology tau such that x belongs to A and y belongs to B. So using this condition, we get A cross B intersection R is empty. Now we are given that the mapping Q from x into x by R is open mapping. By definition of open mapping, image of every open set in X is open in X by R. Here A and B are open subsets of X. Therefore, their image under Q will be open. So Q of A and Q of B are open in the quotient space X by R. Now let us denote Q of A by H and Q of B by K. Now, because X belongs to A, therefore Q of X belongs to H and Y belongs to B. So Q of Y that belongs to K. Now because this is Rx, so Qx belongs to H implies that Rx belongs to H, and Qy belongs to K means Ry belongs to K. Now we claim that H and K are disjoint. We prove it by contradiction. Let if possible H intersection K is not equal to phi. Because this intersection is non-empty, so we can take an element Rz belonging to this intersection. Now by definition of intersection, it means this element belongs to H as well as K. So Rz belongs to H and also Rz belongs to K. Now because Rz belongs to H and Rz belongs to K, therefore we can take elements X star belonging to A and Y star belonging to B such that Q of X star is equal to Rz and Q of Y star is equal to Rz. And now this is Q of X star, that is Rx star. So from here we get R of X star is equal to Rz. Now this is R of Y star, so R of Y star is also R of Z. So we can say that these three equivalence classes of element X star, Z and Y star are same. So from here we obtained equivalence class of X star is same as equivalence class of Y star. So by definition of relation R, this ordered pair consisting of the elements X star and Y star belongs to the relation R. Also, because X star belongs to A, Y star belongs to B, so the ordered pair formed by these two elements that belongs to A cross B. Now because this ordered pair also belongs to the relation, so this ordered pair belongs to the intersection of R with A cross B. But this is a contradiction because we already discussed the intersection of A cross B with R, that is empty. So this contradiction proves that H intersection K will be empty. So thus we have obtained disjoint neighborhoods of the elements Rx and Ry, and these are two distinct elements of the quotient space X by R. Thus we have proved that every pair of distinct points in this space have disjoint neighborhoods. So by definition we can say that the quotient space X by R, that is T2 space. So this completes the Hausdorffness of quotient space.